Okay, welcome to part 4 of the video series on functions as series. Today we have something exciting going on. We'll be looking at natural log 2 and pi as a expanded series. So let's jump in. A quick review of where we were. We started out with geometric series, used a function of the form a1 over 1 minus r, integrated both sides, solved for c, getting 0. We plugged in x equals -1 and 1 to test whether the endpoints converged or did not. And we realized that we cannot include -1, but we will include 1 within the interval of convergence. So if you want to see that in more detail, watch the previous video. Moving forward, our goal is to represent natural log 2 as a series. Now, that doesn't sound very exciting unless you truly think about what it is we're doing. Natural log 2 is some real value, and that would mean that e to that real value is equal to 2. Well, this is a very strange concept, because if you think about what e is this limit. And so what we're asking is, the limit to what power is 2? Well, using property of exponents, we can multiply these two out. And what we're asking is, what value of k satisfies this limit? And so natural log 2 is indeed quite a complex number. It's real number, but the ideas are complex. And what we're looking for is this value k, and it's kind of hard to imagine what this is. So I plugged it into a calculator, and through the TI Inspire, you can actually use this syntax here and get a decimal approximation, or you can get the symbolic solution of natural log 2. So some pretty slick programming from the TI team. And what we're looking at now is there a better way to represent natural log 2 that is not this weird limit notation of a binomial expression? And indeed, because we just saw that 1 can be included in the interval of convergence, we can actually plug 1 in to x here. So we get natural log of 1 plus 1, which creates natural log 2. And plugging in a 1 here, well, 1 to any power is going to be 1. So all that remains is the alternating signs over k. And what you'll notice is that the natural log of 2 is now the alternating harmonic series. So we've now shown that the natural log of 2 is actually equal to the alternating harmonic series. Now this expansion is quite nice to look at. It's a very pretty form, which is a little more easy to see than this form here. Now do keep in mind, if you were to expand this using the binomial theorem, you would also get an infinite series set equal to 2 in terms of k, and if you solved for k using that series, you would also get a series for natural log. Not as clear to do that. I think this is a much more clear method to arrive. And so now we have a series for natural log 2. We do, of course, have a question of, is it a good approximation for 2? Meaning, if we were to take maybe the first 10 terms, would this be a very good decimal approximation for natural log 2? And so I have a chart and some calculator output. I recommend you go through and you practice this notation. So on the Inspire, you can actually type in the summation, store it as a SN function, and then you can just look at the output of the 5th partial sum, the 10th partial sum, etc. And what we see here is, if I look at the 5th partial sum, that's the first 5 terms here added together, we get a decimal of 0.783 bar. If you look at the first 10 terms, that's the 10th partial sum, the 10 of these added together is only 0.64. So is that a decent approximation? Well, what we're asking then is, if I want to know the error, this e of x function, I can store it in my calculator. I want the partial sums given x terms minus the natural log 2. So what is the error between my xth partial sum and natural log 2? Stored as a function of e for error. Well, the error given 5 partial sums is 0.9. Error of 10 is 0.04. So even using 10 terms, we're still at an error in the hundredths And that's not very good. And if you see here on this table, how far out do we need to go to get a good approximation? So you would have to go to the 10,000th term to get an error that is smaller than the 10,000th decimal place. Now, what we say, this is not a very good approximation. You would have to go out very far. So that we say this series converges quite slowly to the natural log of 2. And there's a reason for that. And when you look at the challenge problem on the next page, you're going to sort of go through the intuition as to why this is the case. So moving forward, you're going to apply some of these calculator skills, this idea of error, and you're going to be looking now to create a power series for pi using the series of arctangent. So at this point, you're going to want to pause the video, read through this practice problem. I've included a challenge problem, which is really good at building that intuition about the interval of convergence and error. And if you have hints here, if you don't want to look at them, you can ignore them. I recommend you use them if you get stuck. Okay, so pause the video, and when you unpause, I'll be moving to the solutions page. So here on the solution, we start out with that arctangent series, which is the alternating sign of x values to odd powers divided by the odd numbers in the denominator. And looking at this triangle, we know that the arctangent of 1 over 1 is 45 degrees, which is pi over 4 radians. So the arctangent of 1 over 1 is pi over 4. But if we were plugging in a 1 for x, well, 1 to any power is just 1. So all that's left is the alternating sign over the odd denominators. So alternating sign over the odd denominators. And this should be a 1 here. So go ahead and fix that as a typo on the screen. Multiply out through 4, and we get that 4 as a product, and pi is the product of 4 times the odd numbers. So now, the second part of the solution. Is this a good approximation? Just like natural log 2 took a long time to converge, well, pi also. And when we're looking here, we see 4 times 1 minus 1/3 plus 1/5, ... How far out do we need to go to get a reasonable error for pi? And so same idea. I store 4 times the root of the series, or summation, sorry, of the series as Sn. I calculate S5, 10, 25, ... until I see something reasonable. Now we know that pi is approximately 3.141592653. So right here is my first set of error, this 31415. So I see that 5 is 1/10,000th off, and that's what I'm looking for. So I see the 10,000th partial sum. If I go 10,000 terms out, I'll have an error of 0.00099. And my goal is to look for something with only this much error. So that was a nice guess. And I go 1 less and say, okay, what happens if I go to the 9,999th term? Well, that is still 0.00999999 now. So what about the 9,998th partial sum? Well, now that's slightly more error than 1/10,000th. So I know that I have to go at least 9,999 terms to get the desired error margin. If I go any less, I have more error than is acceptable. So there, 98,999 is the smallest number n where the error is less than 1/10,000th. Quite cool. We will explore how to do this without the calculator in the next video using the alternating series error bound. So stay tuned for that coming out soon. Now for the challenge. Challenge part 1, the same idea. We're going to use that arctangent series. And this time, I'm looking for something that is a value of x that I can plug in. That is going to give me a value of pi. So if I use this now 30, 60, 90 triangle, well, the arctangent of 1 over root 3 is 30 degrees. or pi over 6. 1 over root 3 is root 3 over 3, and the arctangent of that is pi over 6. So that means I can plug root 3 over 3 in for every x. And why do I know I can do root 3 over 3 in for x? Well, root 3 over 3 is in between -1 and 1. It is inside of the interval of convergence. So I can use that value for x, and it will indeed converge to the pi over 6 that I'm wanting. So it's very important that this number is within the interval of convergence. So after you do that, you get a pretty nasty expression. Another nasty expression, you do some algebra simplification, and then you multiply by the 6, and you pull out the root 3, and you get that pi is equal to 6 root 3 times the summation of alternating sign with powers of 3 increasing by 1 and all the odd numbers. Pretty easy to see here as the pattern in the last phase. Now what I did, I left the summation notation version up because maybe you like working through algebra inside of the summation notation, which is just perfectly acceptable and more efficient, or you like seeing the expanded series out and then deriving the pattern from there. Also acceptable. I personally like the expanded version. Okay, so now we have this new series for pi. The reason we don't necessarily see this as often is it's a little messy and not nearly as crisp as the original pi formula we just came with earlier. So now part 2. Is my new series for pi a better series than my old series for pi? And what do I mean by that? I mean, can we approximate pi with better accuracy using less values of the expanded form? So less number of terms. And what it turns out after some investigation, it's a much better approximation. So looking through the calculator, if we store this series in our calculator and we look at S5, well, we are, even with only 5 terms, that's 1, 2, 3, 4, 5, we are already looking at 3.1415. Well, that's not a lot of error, right? So this fifth partial sum is almost within our error margin. So we just go one more out, the sixth partial sum, and we see 3.14159. That's 1/10,000th of error off. So we use that S of 6, what's within the error margin we want. So we know that going 1, 2, 3, 4, 5, 6 partial sums out, the sixth term will already give us the desired error bound. Now compare the sixth partial sum error bound with the 9,999th error bound that we got with the original series. So this series is infinitely better at approximating pi than our original. It's just a little ugly because of these 3's. Okay, so now why is that happening? What's the intuition here? So I've built a Desmos calculator up so we can explore this concept. And you'll see here I've created a new error folder, which is identical to the original arctangent Desmos you have, but now with an error margin. So what we got here, we have the function of arctangent. We have a partial sums notation calculator. So this is one partial sum. So let's go out to about 3, or this is 3 terms. So now what's going on? Well, I can turn on my error. So this is my error function here. This is the syntax for that. And what we're looking at is if you look right here at root 3 over 3, this line indicates the amount of error. Meanwhile, this line at 1, this is the original series that we used using x equals 1, that has that much error. So the series that we use with x equals root 3 over 3 has much less error than the series that we use x equals 1 for. Now that is because as you get away from 0, the center of convergence, and you head towards the boundary of the interval of convergence, the amount of error is slowly going to increase. Now here, we're only using 3 partial sums. Even if I were to increase the number of partial sums, let's say all the way to 30, right? It's still not very good at the end. Thank you.